Okay, good morning, everybody. Good morning. I'm John McGann. I'm in the psychology department here at Rutgers. It's my pleasure to welcome you to the second day of our conference on computation, cognition, and the brain. Order matters. And I'm going to just very briefly sort of frame the transition from the first day to the second day. So yesterday we had a lovely talk from Dan Margolli, who's probably still getting his coffee, talking about how in certain neurons in the bird brain you can see this remarkable degree of stereotypy from firing patterns of one neuron to another, and how that degree of stereotypy relates to the actual structure of the song that the bird itself sings. And that was very interesting because it suggested the idea that intracellular conductances actually can be predictive in some way of the actual ultimate behavior of the bird, not just something at the network level. And then we also had a wonderful talk from Mike Long about networks in a different related structure of the brain, and how some of the seemingly chaotic, I won't say noisy, structure that's seen there may actually turn out to be not nearly as chaotic as it looks, in that it produces remarkably precise physiology, but also that seeming chaos may actually provide a substrate for flexible computation by providing a very varied anatomical structure on which to work. And then in the afternoon, we had a series of talks about data from the LIP and sort of looking in great detail at the signals that are there regarding sort of what the monkey perhaps thinks is going to happen, if you want to look at it that way, or perhaps predicting what the monkey's behavioral decision is ultimately going to be. So that's very much about looking at those signals and trying to think about where in the brain and how in the brain are some of the computations actually being implemented. And so as we transition to this morning, we have a very sort of fundamental subject that grows out of these questions. So the title of the morning session is Space and Time, How Are Simple Quantities Coded in Neural Firing and Stored in Memory for Subsequent Access. So we're going to start to get into the memory issues a little bit more. Randy's our first speaker. He's going to talk about, how could you find if the number 3 were represented someplace in the brain for doing computations, how could you find a 3, and how would you know it if you saw it? And then we're going to have Russ Epstein speaking about the cognitive map and navigating based on landmarks, and how you can sort of infer things about sort of how the representation of the world, if we can use that word after our conversation yesterday. I certainly intend to. And how that can be interpreted in light of the animal's navigation. Then we'll have a break, and then we'll have David Huber talk about a model of memory retrieval in grid cells and what they may or may not be doing. Then this afternoon, after lunch, we're going to then transition to maybe a higher level of representation, as we're going to talk about visual perception and visual statistics, and how the statistics of higher level features may actually be represented and play a role in structuring the representations of the visual world. So I'm going to keep it short and hand it off to Randy so we can get right into the science.
All right. Okay, thank you, John. This isn't the right display. Hang on. Bear with me. There we go. Okay. So I'm going to focus on the fact, the sort of trivially obvious fact, but I think we're not thinking about the implications of the fact enough, that the brain remembers quantities. It remembers discrete quantities. It remembers numerosities. But it also remembers continuous quantities. That's where the space and the time comes in, right? It remembers distances. When the foraging bee returns, it does a dance that tells the other bees the distance of the source from which it's returning. Since we can read the distance off the dance of the bee, it's hard to believe that there isn't something inside the brain of the bee that also encodes that distance. The dance also famously encodes the direction of the source, the solar bearing. So So again, it seems there must be something in the brain of the bee that encodes angles and directions. There's a huge psychophysical literature on in humans and other animals on their memory for areas and other quantities of that nature. I and many others have done a great deal of work on memory for interval durations, particularly with the late John Gibbon, and now I'm fortunate to collaborate with Peter Balsam. That brain also, I've also done quite a bit of work on in the matching phenomenon, in which the behavior is based on the remembered rates at which the animal is receiving rewards in two different locations. And I'm stressing here that rates are numerosities divided by durations. And the reason I want to do that is to call attention to the fact that whatever we're looking for, when we're looking for numbers, it has to represent with equal facility discrete quantities and continuous quantities, because, and then that brings us to the probabilities, because as I'm about to show you, animals down to mice, probably down to insects, also remember probabilities. And probabilities is a continuous quantity generated as the ratio of two discrete quantities. So the representation of both continuous and discrete quantities has to be compatible, as they are, of course, with the numbers that we use in a conventional computer. So just to show that I do experiments, I have to, and also to drive home the fact that animals represent probabilities. This is a recent experiment from my lab in which, there we go. So the mouse is in a box here, and there are two feeding hoppers and a hopper here in the middle. When the light comes on in the hopper here in the middle, that alerts the mouse that it can begin a trial. As soon as the mouse pokes into this hopper, this light goes out and the lights in the two flanking hoppers come on. And this hopper, the mouse has long since learned that this hopper may pay off. It'll pay off on some fraction of the trials. It'll pay off, put another way, with some probability. And if it does so, it'll pay off after 3 seconds. If it doesn't, but the mouse has no way of knowing whether this is a 3-second trial or not, right? The only way it knows that this is a 3-second trial is if it spends more than 3 seconds at this hopper and it doesn't get a pellet, then this is a 3-second trial. At which point it has to leave this hopper and go over to this hopper, and because that means it's a long trial, and after 9 seconds it will get its pellet on this trial. So 3 seconds and 9 seconds are temporal goalposts. And if the animal reliably positions its switches, and what we're interested in is the time after the trial started, at which on long trials, we only get data on long trials, the mouse leaves the short hopper and goes to the long hopper. In doing so, the mouse in effect says, look, I concluded that more than 3 seconds has gone by, and I haven't got a pellet, so this must be a long trial, and I better make it over to the other side by the time 9 seconds have elapsed in order to collect my pellet. So these are temporal goalposts, and the mice, as you will see, very nicely position their switch latencies in between these two temporal goalposts. Is it clear, I hope, to everybody why these are goalposts? Questions at this point? Well, so here are raw data from 5 different mice. The switch latency is being plotted on the y-axis. The trial is on this axis. And the dots here are not spikes. They are switch latencies. Right? And the blue line is the median switch latency. And what you want to pay attention to are the red pluses up here and the red pluses down here. We put a red plus up here on every long trial, and we put a red plus down here on every short trial, so that you can see here that the long trials are more probable than the short trials during this whole stretch. And this, you can just see what the distribution of switch latencies is. And at this point, we make a step change in the relative frequency of the short and long trials. As you see here, if you look closely, you see, whoa, many fewer long trials, many more short trials. Right? And what you also see is a step adjustment in the distribution of the switch latencies. And the mouse, and this is entirely rational adjustment. To use Larry Maloney's metaphor or analogy, if you're doing a free kick in soccer and you think the goalie is going to guard the right side of the goal, then you will shift your kicks toward the left side of the goal. And that's exactly what the mouse is doing. When the probability of short trials is very high, it's really stupid to leave prematurely. So you should shift the distribution of your switches away from the short goalpost toward the long goalpost. And that's exactly what you see the mouse doing. And then here's the reverse step. Now, if you look here, you see, whoa, all of a sudden the short trials are infrequent and the long trials are frequent. Now you should shift your distribution away from the long goalpost toward the short goalpost. And as you can see, that's what the mouse does. But what you also see is that the mouse does this very quickly and very abruptly. That is, you don't see any sort of gradual transition here. And yeah, that's for some reason I didn't think I saw the slide I was expecting. So we did a very complicated statistical analysis to confirm what you could basically see, that these transitions are essentially steps. That is the transition in the behavior itself, shades of yesterday's afternoon discussion. An important point is that on 35% of these changes, as you can see, we made repeated ups and downs. And on 35% of those, because an animal makes a step adjustment in its distribution, we can pinpoint with fair accuracy the trial on which the animal changed. And in 35% of these adjustments that the mice make, the adjustment is made before the animal has lost a single pellet. Keep in mind, if the animal positions his shifts appropriately, he never misses a pellet. So this is not reinforcement learning that we're looking at. And a third point that I don't really have time to elaborate on, and I'm afraid we'll go by, not all the audience by any means, but these adjustments, the latency, the number of trials that the animal has to experience after we make a step change in the relative frequencies, that number is sensitive to the asymmetry in the Kullback-Leibler divergence. That is, if you do an information theoretic analysis, the animal is gaining information about the change, the silent change, more rapidly when the change goes from 0.9 down to 0.5 than it is when the change goes from 0.5 to 0.9. And indeed, the mice make their adjustment, the change in their behavior, sooner when the probability goes from 0.9 down to 0.5, from an extreme value down to a middle value, than when it goes the same distance in the opposite direction. And this is interesting because it rules out delta rule updating, because the delta rule is oblivious to the Kullback-Leibler symmetry. So now, shifting to the continuous, so here we have a behavior that depends upon the relative frequencies, that is, the probabilities of short and long trials. And these trials are distributed over many minutes and hours, and the animal carries its memory from one day's session to the next day's session, and so on. So it looks like there must be a quantity representing, there must be something representing probabilities in the mind of the mouse. And this is intended to show that there's something representing location vectors in the mind of the bee. This is from Randolph Menzel's lab. And they have a hive here. They have one platoon of bees that is into a feeder here. And they have another platoon of bees. These bees are all labeled with little plastic flags on their backs. And they're videotaping inside the hive here so they can see what one bee tells the other bee. So this other platoon of bees is coming and going to this feeder here. And they know, the experimenters know from scoring the video, that these bees have observed the dance of these bees inside the hive. And as I think most of you know, the dance of the foraging bee communicates the location. Well, it's an interesting discussion of how we ought to describe exactly what it communicates. It's usually said to communicate the range and the bearing of the source from which the forager has returned. And in this experiment, on the day after these bees have observed this dance, they arrive here, and keep in mind, there's one set of bees that are going here, and a different set of bees going here, right? And these bees only know about the food here by hearsay, by having observed the dance of the bees. Now, these bees arrive at the feeder, and there's nothing there. They're radar tracking these bees, by the way. There's a radar dish about 10 feet in diameter, and there's a heterodyne reflector on the back of the bee that, so they can radar track these bees out to 1 kilometer. And so here from the radar is a tracker of these bees. So it looks as if the bee has calculated the vector between this location, which it knows firsthand, and this location that it knows only secondhand. And what are vectors? Well, they're lists of numbers. So it looks like, again, there must be numbers in the brain, even of insects. So what are numbers? When I raise this in some workshop meetings, whoa, we get into metaphysical deep waters rather quickly. As many of the people in this room work with computers on a daily basis, so they shouldn't be too metaphysical about what numbers are. Numbers are symbols for quantities. At least originally, that's for sure what they were, right? And as I've just been stressing, they're symbols for both continuous and discrete quantities. Now, of course, they're also symbols for everything. One of the profound, painfully obvious, but seldom commented on lessons from what's happened technologically in my lifetime, which is the rise of the computers, is that we have a machine that was originally designed and is still designed and optimized for the processing of numbers. But that machine represents everything that we know how to represent. There's nothing that we know how to represent in any medium whatsoever that can't be represented by the bit patterns in the memory of a computer. So for me, a number is a symbol for a quantity that refers to a quantity of some kind and that enters into computational operations, by which I mean the basic arithmetic, adding, subtracting, and so on. And the question is, what physically could these symbols look like in the brain? If we're going to go looking for them, what are we looking for? And I can't, just so you see where I'm headed, I observed that we already know that there's a structure in there into which it's easy to put numbers. In fact, at one of my talks, as an introduction, they ran a video of a horse galloping, and the bit patterns that went into that video had come out of polynucleotides, had come out of DNA. That is, the video had been written into bacterial DNA and then transcribed from bacterial. I love that, of course, they drove home the point. So, how are numbers represented in memory? I think this is the most fundamental question in computational neuroscience, period. Because if you're going to design a computing machine, the very first decision you have to make is how you're going to represent the numbers. Because until you've decided on that, you can't begin to construct the machinery that will actually conduct the computational operations that will add and subtract whatever you've decided to use as your physical embodiment of a number. But this is not an acknowledged question in computational neuroscience. Trust me, few years back at a workshop at MIT with 20 or so of leading computational neuroscientists. I gave a short talk in which I raised this, and all hell broke loose. It was astonishing how angry and disputatious people got. But the sort of basic response was, huh? That is, it wasn't as if people leaped to the podium with their suggestions about how it was numbers were represented in the brain. Because it's a toughie. That's the main point of my talk. I'm going to say, let's think hard about what a physically realized number in a serious computing machine has, and what properties does it have to have. And the very first property it has to have is they have to be generable. And this already is an enormous constraint. The idea that the numbers in the brain is now not remotely controversial. And quite a few people, Nieder at MIT being perhaps the best known, are looking at neurons that fire in response to numerosities in the brain. But is this a theory about what numbers look like in the brain? Do we have a 3 neuron and a 5 neuron? Is that our story? Because if that's our story, what happens now when we start computing with these? So we take the 3 neuron and the 5 neuron and we somehow add them, and somehow we generate an 8 neuron. Now, did we take a stem cell and sort of grow it up to serve this function? Did we have an innate supply? Is it like the old-fashioned typesetting before the linotype, that we had a finite supply of 8 neurons, that is, by which I mean neurons that represent 8? And after we've added a certain number of things that come out to 8, we say, sorry, the brain says, sorry folks, can't do this addition, we've run out of 8 neurons. It would be like running out of the E letter in an old-fashioned typesetting. That doesn't seem like a good move to make, right? So if the numbers must be, in a conventional computer, of course, the numbers that are the answer to any computation are generated by the computation itself. It's not like typesetting. It doesn't go fetch the answer from someplace. It generates it. Secondly, the number, what we're looking for, must be able to approximate, that is, represent quantities that range from incredibly small, like probabilities near 0, to incredibly large. The bee works on a range of centimeters while moving inside the hive, doing its dance. But once it gets outside the hive, it forages out to several kilometers away from the hive, and it has this cognitive map that enables it to operate at all these different scales. The Arctic tern makes a round trip between, yeah, this boggles my mind. The bird's about this big. Annually makes a round trip between the Arctic and the Antarctic. It covers 80,000 kilometers every year, flying along the coast and so on. And we know that it has a map of this terrain from displacement experiments and so on. It has to obey Weber's law. We know one of the lovely and surprising things in this whole field was the discovery early on that when we remember numerosities, and we were asked to make a discrimination based on the memory, you see Weber's law. That is, the reaction time, the ease with which you can make the discrimination, depends upon the ratio of those two quantities, so that it's much easier, much quicker to say that 4 is bigger than 1 than it is to say that 4 is bigger than 3. And this is true even in humans, and it's true even in trained mathematicians. I had a mathematician once who refused to believe that this was true of himself. And I said, trust me, as far as I know, hundreds of humans have been run on this. We've never seen an exception, but he was convinced that we took him into the lab, it wouldn't be true for him. He simply knew that 6 was bigger than 5, and he knew it just as well as he knew that 6 was bigger than 3. Another constraint is that they should be noiseless in computation. As Oral can tell you, we go back to analog machines. The trouble with analog memories is, first of all, they're incredibly difficult to build, and second of all, the reading of them is inherently noisy, and therefore, if you plug noisy signals into something, consider the dead reckoning operation that I mentioned yesterday, where the animal is doing a running sum, and he's constantly adding small displacements to a very large sum of his previous, or her previous displacements. If the big sum is noisy every time you come to add, very soon the signal is lost in the noise. So somehow, as in the digital computer, the numbers in the brain have to have this property that the noise doesn't get worse and worse as you run them through successive computational operations. Numbers in the brain have to be signed, directed, right? Because it may be an advanced concept to say that I owe somebody money, but it's not an advanced concept to say I'm going south as opposed to going north. And if the brain uses positive numbers to represent going north, then unless I've missed something, it better use negative numbers to represent going south. And similarly, if it represents positive numbers for a turn in the clockwise direction, a turn toward the right, it better use negative numbers to represent turns toward the left. Numbers in the brain should represent the precision, the accuracy with which the quantities are known. We don't want to be so foolish as to start out with, we don't want the brain to be so foolish as to start out with a quantity that's known only to within 10%, and after a lot of calculation conclude that it knows something to within 1 part in 10,000. So that somehow the brain has to know that you don't gain information in the course of computation, so there has to be a way that the symbols themselves tell you not only an estimate of the quantity that they represent, but how well known that quantity is in fact known. Another big is that they have to be accessible to computation. This seems to be painfully obvious, but this is sort of what I was hinting at when I talked about the 3 neurons and the 5 neurons. That story looks kind of nice if all you're saying is, well, you see, here's the thing that represents 3 because it refers to 3. It fires when there's 3 out there. It's when you start saying, yeah, but you know, numbers don't simply refer, we compute with them. How does the computational side of this story work? And there the things get dicey. And then particularly if you start thinking that numbers are stored in plastic synapses, then in order to make them accessible to computation, you have to have a way of reading the synaptic conductance independent of the presynaptic signal. So the idea of being accessible to computation is quite important in thinking about plausible models. It has to be closed under computation, right? But the brain can't constantly be saying, whoops, you fed me 2 numbers for which there is no number. Now, I'm perfectly aware that in principle, there is an and in every sophisticated computing language because there are operations that cannot be closed, like dividing 0 by 0. But even NAN is really a way of, that is not a number. The symbol that you get when you divide a 0 by 0 is a way of closing the system. And the last thing you want is for the computer to shut down when you try to divide 0 by 0. It should give you some kind of answer, even if it's a very unsatisfactory answer. And that's, of course, what the NAN is about. It should include the operational identities. I won't elaborate on that, but it's got to include 1 and 0. For some people, the idea that there's a symbol for 0, again, puts you back in really deep water. But I'm a formalist. I say, look, if you think about the system, there's got to be a symbol for 0. I mean, after all, what happens when you subtract 3 from 3? Right? Again, closure comes into the argument, right? Are we going to say that, well, when you subtract 3 from 3, you don't get a result because we don't have a symbol for that? I don't think so. So it has to implement both linear and circular addition. When we think about addition, we mostly think about linear addition, but then there's angular dead reckoning, which is keeping track of how far you've turned, and which is an essential part of dead reckoning. These ants, when they're dead reckoning, they're turning like crazy. So you've got to be able to add angles as well. And of course, circular addition behaves differently from linear addition. Circular addition maps the n-bit numbers into the n-bit numbers, whereas linear addition maps the n-bit numbers into the n+1 bit numbers. And obviously then thinking more in just purely physical terms, however these numbers are, what they look like when you find one, the brain has to have some way of writing to those numbers. That is, the quantitative information comes in spike trains. If there's anything we all agree on, I think it's that. And so there has to be a process, whatever this process is that preserves these symbols, it has to be a process that converts, that transcribes from the incoming spike train to the physical embodiment of the number. And of course, there would be no point in writing if you can't read. One definition of a finite state machine is that it's a Turing machine that can't read what it has written. So there has to be a way of converting from this physical embodiment of the number back into the spike trains that will convey that information muscles, but to other parts of the brain, and so on. And finally, I'm a big fan of Simon Laughlin's work on the energetics of brain computation. And the idea that we maintain quantities by reverberating loops, if you start thinking about, well, wait a second, we got to maintain thousands or millions of quantities for decades. I remember the telephone number from when I was 6 years old. I can't resist telling you because it says something about how old I am. My telephone number was 12J. So, you picked up the phone and this nice voice said, hello? And he said, please give me 12J. And okay, so I don't think that's been kept going by a reverberating circuit for all these 70 odd years. Right? So, and I think there are gigabytes worth of these numbers in any respectable brain. So the physical realization of them better not take up a lot of room. Okay, where to turn for guidance? Well, I think it's obvious from what I've been saying. Well, I'll say, well, where do we, is there a field where people have really been worried about how you physically represent numbers? And of course, that's computer science. And there's an interesting lesson here again. Von Neumann said, guys, back in 1945, he told the ENIAC people, you should use 2's complement. It turns out, I thought, well, how original? How do you know about 2's complement? But it turns out, adding machines, going back to the start of the mechanical adding machines, were already using 9's complement, and 2's complement is just the same idea carried to a different base. The great advantage of the 2, I'm not going to explain the 2. I tried once in a talk to explain 2's complement. It was a disaster. But I'll just tell you what's great about it. 2's complement, if you already have a mechanism that will do addition, if you're saying, okay, good, we can do addition, now how about subtraction? What do we do with negative numbers? 2's complement is a way of representing negative numbers such that the machine that does addition will work with those. So you don't have to build another mechanism that does the subtraction. Okay, the interesting lesson is that despite the billions of dollars that Intel and all its competitors have invested in the design of the fundamentals of computing machines, when it really counts, when you want low energy and small space and so on, the 2's complement fixed point scheme is still the one that's being used. So what that tells us is, well, there may be alternative good schemes, but they aren't easy to think of. And so I doubt that I'm going to be better than the legions of engineers at Intel over all these years, or at IBM with their neuromorphic chip. Okay, so now at what level should we look for the physical embodiment of neurons? I already made some fun of the idea that they're embodied in individual neurons themselves, but almost all computational neuroscientists assume that memory, the medium of memory, is altered synaptic conductances. how would that work? Well, it's not that you can't think up a story. I've got in my back pocket 2 stories that I can tell you about how you could do that. But I've never found anybody who was willing to embrace either of those stories, at least in print. And I've never found anybody who could produce a 3rd story. So altered synaptic conductances don't look too promising to me. So what does look promising? Well, I put it in red. Molecules, right? As I said at the beginning of my talk, we know how to write numbers into molecules, polynucleotide strings. These cells are full of microRNA. The microRNA can bind to proteins and alter their enzymatic activity, so that provides a reading mechanism. I have no clue of what the writing mechanism might look like, but I do think I have a Stirling and Laughlin on my side, because when you shift from the cellular and the circuit level to the molecular level, Feynman's old dictum about there's a lot of room at the bottom comes into play. You gain at a step 8 or 10 orders of magnitude in both volume and energy requirements. So for example, when you're maintaining a quantity, as is often suggested in all the moving bump models that are out there these days, where the nervous system is supposedly maintaining a quantity by constantly circulating a spike train, you should remember that the brain has to hydrolyze 10 to the 8th ATPs for every spike, right? So that is, spikes are not cheap, right? So this is a mind-bogglingly expensive way to try to maintain a quantity in this machine. Now you might say, well, maybe ATP is such a small unit of energy that nothing interesting can be done with 1 ATP. But in fact, the cost of adding 1 nucleotide to a polynucleotide train is exactly 1 ATP, right? So if you move to the molecular level, suddenly, wow, the energy here required becomes many, many orders of magnitude less. And so does the compactness, right? You gain about 15 orders of magnitude in the amount of room per bit that you have to use if you move from the circuit level to the molecular level. Okay, I want to get on to the next slide. So I think many people in this audience realize that with a little thought, if you understand polynucleotides, it's not hard to see how you write numbers into polynucleotides. And you almost immediately see that, hey, if we do this, RNA, like DNA, complementizes, right? And the complement of an RNA string is the bit flip. And the bit flip is the first of 2 operations in taking the 2's complement of a number. But moreover, of course, once you have the complement, then you synthesize the back complement, so to speak, and you've made a copy. And copying is an incredibly fundamental and important operation. When the foraging ant goes out and finds a bit of food, it goes directly home. That's the evidence that it knows where it is by dead reckoning. What's not often stressed is that when it next emerges from the nest, it goes directly back. So it has copied the location coordinates at the time it found the food into a memory bank that enables it to return. Okay. So what I'm saying is that what we should be looking for is a molecular realization of 2's complement fixed point numbers. And the necessary corollary of this is that we've been looking at the wrong level of structure in our computational theories all these years. Because if the memory is inside the cell, then at least it would be madness to put the computational machinery outside the cell. So I'm a big believer in, where's this quote? Anyway, somewhere I have a quote from the Laughlin and Stirling and Laughlin book, Principles of Neurodesign, a wonderful book, strongly recommended. And they summarize it as follows. For a variety of considerations which they list, compute with chemistry. It's cheaper. Many, many orders of magnitude cheaper. Okay, so now I'm going to ask the question. I know most of you are thinking, this is crazy. He can't be serious. And that's what, so I hope I left time for a little discussion about why this is crazy. So, the floor is open. Okay. This way. Yes, Mike.
Couple of questions if you don't mind. So if Weber's law is important to understand the neurobiology of numerosity, then doesn't that rule out computer science as an inspiration?
No, not at all. Fixed point numbers obey Weber's law. Fixed point numbers divide. That's what I didn't have time to unpack that. But in fact, there's a proof now in the literature that any effective magnitude representing scheme that uses limited physical resources to represent quantities over many orders of magnitude must obey Weber's law. But the fixed point two's complement does obey Weber's law because it divides the representation into a significand, and the number of bits in the significand is the precision, right? That's how you know how well the quantity is known, and that you can control the precision by varying the number of bits in the significand. And the exponent. And the exponent sets the scale, right? And the significand tiles the ballpark that is set by the exponent. It obeys Weber's law.
Weber's
You get it for free.
It doesn't tell you why it takes more time to tell 4 versus 3 against 4 versus 1.
That's true, it does not. I mean, I have a very speculative story about that, but you're right. I mean, you don't get that explanation for free, that's for sure.
So when you see that an animal uses bearing and distance to do the Waggle-Dance, yeah? You say that, or whatever it's communicating, the bee, then you think that therefore there must be a number stored that corresponds to these kinds of quantities. But why not just think that what the bee does is parameterize the Waggle-Dance? Why does any
parameters are numbers, right?
Parameters are states of a circuit. Why do we assume that the animal has explicit representation of the quantities that ultimately are communicated to the dance, as opposed to just establishing the dance itself?
Because I don't understand how, on that scheme, it computes the resultant vector. That is what I showed you, is that it has 2 locations, somehow represented, right? One just by hearsay, one by direct experience, and it can compute the resultant vector.
Okay, that's a little different. I mean, that means that's how you interpret the Waggle-Dance. And I agree that's an interesting problem.
Well, you saw how he flies.
But that doesn't require a memory. So the interpretation, it still doesn't require an
Sure it did. That is, he had heard about the hearsay was the previous day. That is, the knowledge about where the other food source was had been acquired under totally different circumstances, inside the hive where it's totally dark, from a dance conducted by another bee running vertically on the hive wall, the previous day.
Right, I guess I'm suggesting that even that knowledge is sort of implied in the plan to fly someplace.
Well,
it looks like vector subtraction.
All I'm saying is, you've got to run the computation. It's not enough to say, okay, here's what does the referring. Okay? You've got to say, how does that symbol, whatever you want to call it, parameter, that does the referring, how does that enter into these arithmetic operations? Yes, David?
Yeah, I have a thought that may bring together these 2 points of view. Because as I think about the bee flying out, and you know much more about this than I do, so don't tell me I'm wrong early in what I'm saying. It expends a certain amount of real energy to fly there.
For sure.
Right? And in some ways, that energy expenditure is related to how far away it is.
For sure.
You can imagine that there is a metabolic marker for how far it is, which we can interpret as a number representing kilometers.
Right.
Okay. Similarly, or by similar kind of reasoning, the mouse waiting for 3 seconds or 9 seconds, that elapsed time, it's learned if I've been here for 3 seconds, there's something is counting, but it is also the passage of either metabolic time in the sense of energy that's been expended, or the operation of intracellular clocks, which we know are ticking all the time, and which may accumulate, because they are in fact stored in numbers of molecules, not necessarily in RNA, although RNA may be tracked in the number of molecules that are made. So there may be, within these examples, physical operations of the body and the brain which encode the things that we're calling numbers.
Maybe there must be.
Yes, that's the first half. And the second half is the RNA system, or something like what you're proposing, may in fact be tracking those actual behavioral events or the spiking of neurons with some information that's coming into the visual or auditory system, so that we can have something which fits Mike's idea, which is it's kind of like this is the animal doing the behavior, and the notion that there's a numerosity encoded as a kind of molecular byproduct. Is that a way to think about it?
Well, again, I keep hammering on, I got to see what the computational story looks like, right?
So it's your story of the RNA.
No.
The RNA is tracking the behavior, not some abstract number, except it is embodying that number as much as any computer embodies that number.
Yeah, but nowhere in your account did it compute the result vector or do change detection that was sensitive to the Kullback-Leibler asymmetry, right? Now, to me, those reek of numbers. I've got to see what any story, I guess this is the take-home message, any story about how numbers are represented in the brain has to focus strongly on the computational side of things. And I think the accounts that both you, David, and you, Mike, are offering are like all the others out there. They focus only on the referential side. So you're talking about there have to be transducers. For sure there do. There have to be integrations, for sure. Of course, that's already a computational operation. I mean, the odometer of your car doesn't measure distance, it counts wheel turns. This is the way you estimate things. In the old days, you didn't measure the speed of the boat. You threw a log over the side and you looked at how many knots you ran out by the time you got to the back of the boat. Yeah.
In school, we teach numbers before we teach vectors.
Yes.
I would like to posit that in the nervous system, numbers are represented as a special case of vectors.
I agree with you. Totally. Numbers don't really come into their own until you get to vectors. And
vectors, we know how they're represented. Because like in the visual cortex, orientation is represented, we know how to add them. So,
do we know how they're represented in memory?
well, I mean, on the short time scale, they're represented in the neural activity and maybe
Yes. I'm trying to move the focus away from the short time scale, right? I'm a psychologist. I'm interested in the long time scale, right? Hours, days, 12J in my head after 70 years.
To add, I cannot, I add on the fast time scales, I don't add on the slow time scales.
Yeah. But dead reckoning.
It cannot be on the molecular level.
But dead reckoning in a migratory bird flying from Nova Scotia to Argentina unfolds on a scale measured in days.
Of course, right?
Yeah, so that means adding all that time, right? So,
Do you think there's a connection to all of our biological clocks?
I'm sorry?
Is there a connection between what you just said and our biological clocks that work on many scales?
Well, who knows? But of course, the interesting thing about them is that they turned out to be implemented at the molecular level. But, by the way, when I was a graduate student, the idea that there were biological clocks was extremely controversial. I was in a beer thing with my fellow graduate students once, and of course, I was arguing there were, and one of them said, "You mean if we took the skull off, we'd see the hands going around?" So, so the idea that there was a clock in those days was unthinkable, at least to some people. And yet it turns out there is, and we all agree about that now, and moreover, and most importantly, it's implemented at the molecular level. So I draw lessons from that. Let me get some I'll get you to see you.
Actually,
Oh, yeah.
we can hold off on questions
Until later, yeah.
after the next talk. And there is time in the schedule.
Sure.
After we've had all 3 talks, we have a meaningful amount of time set aside for open discussion. So please save your questions, especially if they can potentially tie in across speakers.